Hey, this is Steven from LegitTechTutorials and the Green Engineers, and welcome to a new episode of a new season of my product development series. So we are going to be doing a new project, and this one is another, I guess you'd call it, production machine. So it's a one-off production machine. And so it is a heat treating oven, so a heat treating steel to make it harder and thus take more load to get it to deflect the same amount. So to increase the stiffness of a material, basically. So there are multiple different heat treating ovens that you could buy, and so there's generally two different kinds. There's either electric, or there is propane fired or some other fuel fired kilns. So electric kilns generally are more, as far as personal use, not really like big industry, but personal size, like the Even Heat right here, which we can see Even Heat. So personal size ones like this, generally they're pretty popular to have the smaller kinds of kilns or ovens. So here's a glass kiln, ceramic kiln, knife, heat treating ovens, blah blah blah. So obviously we're looking for night or heat treating ovens, and we are probably going to either use a 110, probably a 110 volt series, and we need it. We're looking at a basic spec, so let's go ahead and add a specs. Well, we'll talk about that later. First we'll spend some time. We'll talk about that in the next video, because that's usually what I do. So here are electric ones. All these are electric, no propane fired. As you can see, the resistance wires inside. This one right here is very interesting. I haven't actually looked on Even Heat in a while. I don't remember seeing these. These are salt bath series, which that's actually a pretty good idea. So we'll talk about those ones also. So you have these guys, and then you have propane fired kilns, and so this is kind of the size that we're looking at. So kind of like a small personal one. So we have 18 by 10 by 6, 22.5 by 10 by 6. So usually they're very deep, not very tall. They're wider than they are tall. Or you have something like this where you're trying to heat treat like a sword or something. So very deep. Obviously past 27 inches, so it's probably like 50 inches. So it's like doing a sword or something. And so let me show you one of the reasons why I was going to design this. Usually it's for the price, and design one with your type of So yeah, so generally these are about $1,000. So now let me explain why these generally are kind of have a problem. So number one is usually because they are very big. What you have is you have something called decarb happen. So when you place steel inside, steel is of course made of carbon and iron, right? Basically what heat treating is, which I should bring up a wiki, because again, I'm a mechanical engineer student at San Jose State, so here in San Jose, California. So one of our classes we learned about material science, intro to material science. You learn about this kind of stuff. So basically what heat treating is you diffuse the carbon out of the mixture at the can't remember. There's a specific austenite. The austenite temperature point, which for most steels like 1500, 1600 Fahrenheit, the carbon diffuses out of the mixture with the iron and floats around inside of the steel. Then after you have that completely dissociate, such as that, you take it out and you quench it in a bath. And then there's a certain amount of time, depending on the carbon content of the steel, that you have to take it out and quench it, drop it down to below a certain temperature. There's different graphs of that. It's kind of like a weird looking, like recessed mountain looking thing where you have like a round part of the mountain, and then it's like cut back. So you have to quench it quick enough, get the temperature low enough that you don't hit that little like nose point. So the other issue is that when the carbon diffuses out of the material, sometimes it also diffuses into the environment. If the environment does not have as much carbon carrying, something that's going to help carburize the steel, what's called carborize, then decarburize the steel. If there's more that's there to decarburize the steel, the carbon will actually diffuse into the environment that it's in. So basically when it comes out, it's very difficult to heat treat depending on the thickness, right? Because only a certain amount of the surface could decarb. But yeah, it's going to affect the surface, so the surface isn't going to be as hard, and it's going to be difficult for you to determine whether your heat treat was successful. Because inside the steel, it could be hardened, but outside it will appear that it's not hardened. So you can't really tell if the inside is hardened unless you're going to cut it open, but then you're destroying your part, so there's not really any point in doing that. So usually you use what I have also is what's called hardness files. We have different Rockwell ratings. So there's different ratings of hardness, which could also be associated with stiffness or strength of a material. And so what they have is they have different files that are rated for different hardnesses. So if you file your material with let's say a Rockwell 50, and it gouges it and it starts to file, then that means that you have a steel that is not as hard as a Rockwell C50. But if it doesn't, that means that it's a higher one, and then you would use like a 55 file. If that doesn't file, then you'd use a 60 file. And then if that files, then you're between 55 and 60. So you do stuff like that, or you do like a Rockwell tester where they have a diamond press, and it presses in, and it will basically see how much force it takes to press this diamond rod, or this diamond like kind of point into the steel. Or you could do other types of home things where you build like one of them is you have a tube with a ball bearing, cut a slot in the tube so the air could escape, and then you drop the ball bearing, and it will hit the material, and depending on how much it bounces, you can tell the hardness of the material. So if it doesn't bounce at all, that means it's a soft material. If it bounces really high, it almost returns. Obviously it's not going to return back to where you started from, because you're going to lose some in friction, sound, and heat. So you're going to drop it, hits the material, comes back up. The closer it gets to coming back up to your original position, the harder the material is. I'm personally using files. So the issue is that we have a kiln in the Redwood City Tech Shop, but it is a small electric kiln, and you'll actually have some problems with decarb because there is a oxygen-rich environment and not an environment that is promoting carbon or any sort of other something like ammonia, or if you're doing nitriding or whatever. So if it's an oxygen-rich environment, it's going to start to decarb, where the carbon inside the steel is going to diffuse into the rest of the diffuse into the environment inside the oven until it reaches an equilibrium. So it's basically going to diffuse out and then stay there. So when you pull it out and you quench it, you can't actually tell whether the heat treat took or not, because the surface will still be soft, but the inside of the material could also be still hard. But you don't know, right? You don't know because you're filing the surface, and you don't know. You know that the inside of the material might be harder, but you don't know how hard it got. You don't know how well the heat treat took. So that's number one. Number two. Generally, the taller the oven, like the one at Tech Shop, is not very deep, but it's very tall. And so what will happen is the heat just gets trapped at the top while generally it parts at the bottom. So there's no circulation inside of the electric ovens. So it doesn't push the heat around to kind of meld it, better. So push the heat around. And also sometimes what they'll do is they'll have which is exactly here, you see that the thermocouple that's reading the temperature is in the top of the kiln, where the temperature at the top and the bottom are two different things. So this one maybe not so much because it's not as, it's only 6.5 inches tall, so it might not be that different. But in one like at Tech Shop where it's a foot tall, it's quite a bit different between the top and bottom. And the thermocouple's in the top, so it's thinking that your temperature is good at maybe 1500 Fahrenheit, but at the bottom you're actually at like 1200 Fahrenheit, let's say. Because heat rises, so heat just gets trapped at the top, because there's nothing that circulates it around. So we'll talk about that problem later. So those are the two problems, decarbing and also the heat spray. The heat getting stuck at the top when generally it parts at the bottom. So then you have another one, which is we call it a coffee tin forge. So here's a coffee tin forge. So basically these are old school. So this is a flame or so it's basically a fired kiln. And so these are old school. They call them coffee cans. So they're made out of like coffee tin, or you see like a gallon paint bucket. Sometimes they're made out of. Basically, what these are kind of like ceramic, a ceramic mixture of perlite, or some people even use like kitty litter, or plaster of Paris, or any sort of ceramic that will withstand a lot of heat. Also, another thing that it will do is it will hold its heat for a long time. So basically it won't absorb the heat that you're pumping in there, because it heats up very slowly. So it won't absorb a whole lot of your heat, and it will radiate a lot of your heat. So you have a hole here, you stick your torch in there, and then you push. This is a propane torch. It's a handheld propane torch, or you can have, there's different types, but yeah, like this, like a handheld propane torch. And then you put that in there, and also another thing you have is like some sort of fiberglass or something, and then a steel piece in here that keeps the fiberglass there. And so you have this firing, so you fire it, and then you have the front and the back. Back is, so I guess you could say you have intake and exhaust, so where air comes in to burn reduce, I guess. I can't remember if it's reducer or oxidizer, I can't remember. Not oxygen, I think it's a oxidizer. It is an oxidizer, that's why, oxygen oxidizer. And then, so you have an intake for it to oxidize propane to allow it to burn, and then you have an exhaust where the heat comes out. So also it kind of shares in this point. So generally you don't see one that has open on, not open on the backside, but this one might be that way. That one also might be that way, but generally you have them open on both sides. This one's also that one's also not. But yeah, so you get the idea. So something like that also is another one. So now this one does not have the same problems as well, this one has its own problems, but it actually has different problems than the electric kiln. So this one, of course, it uses propane, while at Tech Shop it uses if it would be at a Tech Shop, it would be made using electricity, which the electricity is included inside of my membership, so I basically don't pay for the electricity. So it has consumables, right? Also dangerous consumables, like you could drop it and it break the stem open and shoot across the room or whatever, hurt somebody, or explode, or puncture and then light on fire and then explode and stuff like that. It gets really hot. It's very efficient as far as getting hot. I mean, obviously it leaks a lot of, it's definitely not efficient because it just leaks all the heat out compared to electric kiln where it holds all the heat in, but you can't have it hold the heat in and have it fire inside, because basically it runs out of oxygen, right? Because it turns it into, let's take a look at the actual chemical reaction of propane and oxygen. So here's propane, here's oxygen. It creates carbon dioxide gas, water, and heat and light. So let's look at decarb. Is a process opposite to carburization, namely the reduction in carbon content. This term is technically blah 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 carbon heated or above when carbon, the metal, reacts with gases containing oxygen or hydrogen. The removal of carbon removes hard carbide phases, resulting in a softening of the metal, primary at the surface, whereas in content with decarburizing gas. So here's a chemical reaction. So the most common reaction is with carbon and CO2. Carbon, water, carbon plus H2. Other reactions are carbon plus O2. So for example, in a regular kiln you have a lot of O2, turns it into CO2, which obviously is not breathable. So that's kind of a toxic, quote-unquote toxic gas if you're in an enclosed environment. And then you have carbon plus iron, iron oxide is carbon monoxide plus iron, so that's definitely not good. Carbon monoxide. So C plus 1/2 O2 is equal to carbon monoxide. This is methane, carbon CH4, I think that's methane. Anyways, I can't remember. Methane. Wow, I took this class a long time ago. I'm pretty good. I guess I'm pretty good at remembering it. Anyways, so yeah, methane CH4. Carbon plus water is COH2. So it's pretty weird that this chemical reaction has carbon and water, and yet it doesn't have a problem at decarbing. Probably because that kind of equilibrium is changing all the time, and so it doesn't happen. So what I would like to do is also another thing with so obviously there's not a problem with decarb generally. There's not a problem with heat getting stuck at the top because it is swirling with the propane torch, right? So that's not a problem. But the issue is controlling temperature and also production, right? Because generally when you look at these guys, the coffee can forge or anything like that, this is one blade at a time. This is one thing at a time. You can't do a whole batch of things. So you can do that in the electric kiln. So here you can't do, not very great for production. There's not really any temperature control. Basically what you have to do is you have to judge it by color and take it out and quench it. So it's not consistent. It's not replicatable throughout an entire batch of stuff. And there's no control of the temperature, and also it uses consumables that Tech Shop will not cover. So, what we're going to do for this one is, because of rules of Tech Shop, which I'm going to talk with the GM, the general manager, to get some more specifics on this. Now, if I have to, I'll do it at Redwood City. Redwood City would definitely accept it. But for Tech Shop San Jose, generally we do not do open flames. So propane kind of out of the question. So for continual use, maybe once, yeah, sure, they might get away with it. But continual use, you know, and be okay with the general manager and everybody else there, probably not. So generally we don't want open flames. So that leaves electric, which most of the stuff for electric is ideal for production, which is what I'm going to be using it for.
So we have good temperature control, except for the top and the bottom. And then we have to solve that problem. We have to solve the heat spreading from the top and the bottom, and then we have to solve the decarb problem. So I've been thinking about this for a while, and I think I came up with a solution to do this. So what we're going to do is we're going to kind of combine the two, the best parts of the two, to get a production electric kiln, heat treating kiln. So, and also if you didn't know, this project is for the shredder project, the Green Engineers product, the shredder, the reclaimer I call it. So the shredder blades harden the shredder blades so they hold an edge longer to cut plastic. So basically harden these shredder blades. Right. So this was the idea that I came up with. So it's going to be electric kiln, but be casted like a coffee can forge, like you see here. So this one, it uses like plaster of Paris and a mix of other things. So sometimes it's sand, which, sand is a ways, to get sand, or you have to buy it. While we have garnet that we use in the water jet. So maybe I'll just grab some garnet from the bottom of the water jet and mix it. So come up with our own kiln mixture so that we could actually cast it instead of buying fire bricks, because that would be a lot cheaper to build than to make it out of fire bricks. Because usually electric kilns are made out of fire bricks. So that would be quite a bit cheaper to build. And also pretty interesting. I don't know if I've seen a casted kiln that's for electric. And also it would be a lot easier than carving into the fire bricks and create a big mess and cleaning it up and stuff, instead of just casting the stuff right into it. So that being said, so casting a kiln, so obviously square kiln instead of a round kiln, so we can stick a lot in it. Electric fired, so we're going to have a thermocouple in the bottom. And this is how I plan on solving the two problems and what I've come up with. Of course it always changes when I start designing. I see something that's not going to work and I change it. But this is what I've been thinking about for this solution. So for the heat from top to bottom, so you can't use electric plastic fan, because it'll instantly melt the plastic fan. You're talking about 1600 Fahrenheit inside that furnace or inside the kiln. You can't, even if you did get maybe electric fan with a metal blade, electric motor with a metal blade. It's so hot in there it will demagnetize the magnets instantly, and then your motor's fried. Obviously, it's going to fry the silicone that's covering the wires. Wires going to short out, and then even if it doesn't if it does that before it demagnetizes the magnets, it just doesn't work anymore. So whatever it uses is going to have to be a mechanical. It's going to have to be a mechanical operation. So I'm thinking of a mechanical fan that will push the air from the top to the bottom, because this is going to be a decent sized kiln, and we'll go over that in the next video coming up. So now what I was thinking is, okay, how can we combine these two issues and take care of two issues, the decarb and the pushing from the heat from the top to the bottom, and then get them all in one solution. So kill two birds with one stone. Finish off those two problems with one solution. So I need a mechanical fan, and it needs to be driven by something. So another thing that I would like to be able to do is be able to do different sort of gas, carburizing or nitriding of the metals inside. So let's go back to carburizing. So carburizing, there's a few different methods. Another one of the methods is, which will also take care of a lot of this, but it's kind of really caustic, because I'll show you guys in a second. But it's basically this salt bath. Salt bath is another way that you could harden stuff, but the issue is getting proper salt bath where it's going to not just boil over, and so because you know water boils at 100 Celsius, you can't get it much bigger than that. But, so something like this, a salt bath. Let's go ahead and see what that says. Before we see what that says, let's look at carburizing. So there's different methods. Carburizing of steel involves the heat treatment of metallic surfaces using a source of carbon. Carburizing can be used to increase the surface hardness of low carbon steels. So for example, you could use a lower carbon steel, harden the surface so it acts like a hard steel, but yet the inside still be soft, so that it's not as brittle, basically. So we have a different, different method. So early carburization was a direct application of charcoal. So this is a way I would call packing. So you could pack charcoal around your part, and then that will diffuse the carbon out of the charcoal and into the metal part. This could still be used, but it's going to give off a lot of gas and stuff. So initially referred to as case hardening. But modern techniques use carbon-bearing gases or plasma, such as carbon dioxide or methane. The process depends primarily upon ambient gas composition and furnace temperatures, which must be carefully controlled, as heat may also impact the microstructure of the remainder of the material. So basically, to not decarb, we just need to have an environment where the carburizing gas is higher than the decarbing gas. Another thing that it says down here, stainless steel, carbon dioxide, blah blah blah, furnace. So plasma carburizing, obviously way out of our range here. But they have another one where it's basically salt bath. It's a salt bath carburizing. So salt bath quenching, right? So basically, oxidizing temperature fast enough to avoid the perlite nose. So like I said, the nose. And the material's time temperature transformation diagram. And to transform the austenite into martensite to the maximum extent. So it's like a nose thing, and it has a backward slant, and you have to basically drop the temperature of the steel so that it misses the nose. So basically, salt over oil. The most of salt over oil is a wide temperature range. Salt bath quench. So this is not the correct one. We're not talking about salt bath quenching. We're talking about carburizing, where basically you superheat these liquids, and the solution has carbon-bearing compounds that will go into your material. Into a bath of molten salts. Once immersed, the blade quickly reaches the properly hardening or quenching temperature. The blade is then allowed to soak in the bath for the amount of time you desire. Once the soak is complete, the blade is pulled for further quenching and processing. Salt bath process provides an oxygen-free environment, so there's no need to wrap the blades, and temperature distribution around the blades is phenomenal. So what they mean by wrap the blades is put the blades in something so it doesn't decarb. While the salt bath process offers advantages, it does come with some hazards, notably the possibility of the molten salts erupting from the salt pot vessel that contains the molten salt. This creates a burn and fire hazard, as well as risk of personal injury or death. These changes, okay, special temperature salt to thermocouples to control proper heat. Additional features include drip shields on both salt baths. So yeah, basically also the salts that you use could be very caustic. It could be very hazardous for people and stuff like that. So what
So we generally can't do that. So we can't do that. We can't do plasma. We generally don't want to do solids because then you have to buy, charcoal. There is one way that I was thinking of getting hold of charcoal, and that was through pellets, but I don't really want to do that. So basically we have the option of using gas. And so here it says that you can use carbon dioxide or methane, but here in our chemical reactions, not for propane, so here's the most common reactions are carbon plus CO2 is 2 carbon. So let's look at carburizing reactions. Carburizing gas reactions. So in the gas carburizing process, a low carbon bearing carrier gas is used, which is enriched with a hydrocarbon gas such as propane or methane, natural gas, to increase and control the carbon availability in the atmosphere. The carrier gas is usually of endothermic gas type, blah 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 blah. Okay, depending on the type of carbon in the mixture, the typical composition of the carrier gas is 15 to 25% CO, carbon monoxide, 35 to 45% hydrogen gas, and nitrogen gas, plus small quantities of CO2, H2O, or methane. So these are basically your carbon carrying gas and carbon monoxide. The gas carbon monoxide and methane are carburizing, whilst H2O, hydrogen gas, water, or carbon dioxide are decarburizing. A hydrocarbon gas according to the reaction. So here's methane plus water plus carbon monoxide plus hydrogen gas. So here's methane, carbon plus iron plus 2H2O. So here's the carbon inside of the iron. So basically what it's saying here is that the carbon monoxide and methane are carburizing, whilst H2O, H2O, and CO2 are decarburizing. So here's another way of using oxygen probes to figure it out. So basically what I'm getting at with this is that instead of using, so I want to be able to control that, and also another thing that we could do is carbon nitriding, which I'll show, nitriding, which I'll show in the next video, which is you use ammonia, which is also not really the greatest gas, but for use inside of a confined space safely. Anyways, it's similar to carburizing, but slightly different. So what I want to be able to do is be able to have a gas inside of a small container and be able to pump it inside of the container, inside of the kiln, at controlled quantities to be able to control the environment inside of the kiln. While normally you cannot control the environment inside the kiln. Obviously it's going to decarb until it gets to a point, reach equilibrium, and then just kind of be there. So also be able to carburize. So if I wanted to elevate the amount of carburizing gas versus decarburizing gas, I could pump more in there and pump the other stuff out. So I was like, how can I combine these two things of using a metal fan with a mechanical motion and this gas? So generally, when you get a gas inside of a canister, it is highly compressed. So it's compressed a large amount of moles of the molecule inside of a very small volume. So obviously pressure, P versus V, pressure is very high, volume is low. Well, volume it takes up is low. But because the pressure is high, that leaves a large potential of energy use. So what I was coming up with is if you take the gas inside of a small canister and you expanded it inside of a piston inside of this kiln to move the fan. So basically you have sort of like a steam engine piston with a crank driven fan inside of the kiln
to pump the gas from the top, or to push number one, to push the air around inside to give even heat distribution. And number two is to introduce carburizing gases and deintroduce decarburizing gases. So basically a cylinder with a piston with a crank driven onto a fan that will rotate the fan. And so basically you have that inside the kiln. So there's not a lot of heat leakage because it's inside the kiln. Then you have a tube that is sealed that's attached to the fan, high temperature, some sort of, probably going to be some sort of metal. And then seal that off so you don't get a whole lot of leakage. Obviously there's going to be stuff, it's going to be leaking up through there. So it's going to be really hot. And then be able to pump that through that tube into the canister and use that reaction of basically take the energy that the company that pushed the gases into the canister, take that energy and move the fan, and then use that gas inside of the container. So this is going to be one of my few videos where we're actually going to use some engineering mathematic principles to look at those different types of reactions of how big the piston is supposed to be, how much power are you getting out of it, how's the temperature going to drop when you expand it, how much volume is this going to take up every time, blah blah blah, etc. etc. So basically, again, piston with a crank, and then have two valves, inlet valve, outlet valve. And so one will let the gas in, and then one will let this excess mixture out. Right? So yeah, so that's basically the idea. So altogether, summary: electric kiln with maybe top and bottom thermocouple probes, top and bottom, to determine when to spin the prop. Also maybe oxygen sensor inside, how it says to control inside the kiln. So definitely more sensors than normal. Top and bottom thermocouple, oxygen sensor, microcontroller that controls everything. The heating and cooling of the electric elements, reading the oxygen sensor and the two thermocouples, and then being able to open up this valve, a high pressure valve that lets either ammonia or methane or carbon monoxide into the chamber, and read when that has diffused into the metal and allow it out, and then let it out. And also monitor where the piston is in order to get the reaction right. And so basically set up timing by reading probably a pressure gauge. So I have some sort of pressure gauge readout that will, and also actuated valves that would open and close. Or those would be always open, one of the two. Each side would always be open. And so almost like a two-stroke engine. It's basically an engine, two-stroke engine. So have this move back and forth and have it let gas in and then let it come back, because basically it's going to be as heavy as a flywheel. So it pushes the piston back, and then it introduces again, pushes the piston back, so blah blah, etc. So it needs to be able to control all that. So now we got rid of basically all our problems. We have a large production area for production of materials, carburizing, as well as heat treating. And also this could be used for tempering, because if it could hit 2000 Fahrenheit, it's going to be able to hit 700. So large production area, even heat distribution with temperature control. Then we have a carburizing gas, so no decarb, and repeatable every time, and a go-to. Also, preferably as safe as we could get. So that's pretty much it. In the next video we'll go over the specs and how we're going to be doing all this stuff, and what things to look out for, and different manufacturing processes that we're going to use. And that's basically it. So this is it for this video. We're going to go more into depth about these different ideas that I have, and the different types of manufacturing techniques as the video goes on, and especially in the next video.
So I'll see you guys in that video. So this has been Steven from LegitTechTutorials. I'd like to thank you guys for watching. If you like this video, please subscribe for more videos like this series and other series as well. I'll see you guys in the next video. Thanks for watching. Take it easy. Peace.